Welcome back, AP Chem. Today we're going to be starting in Unit 2 of our class, so we're already through Unit 1. Hooray! And Unit 2 focuses entirely on bonding. So we are going to focus on 4 different types of solids, essentially, that you're going to encounter. You're going to encounter ionic solids, which we'll be talking about first, then covalent solids, then we're going to talk about metallic solids briefly, and network covalent solids. So there's lots to kind of dig into in the next couple weeks. And so we're just going to get started right off the bat with what bonding is and why it happens. So if you go out and take a walk outside in nature, it is very rare that you are going to come upon a sample of an element just by itself in its pure elemental state. Gases, sometimes maybe you find them, but oftentimes most elements come along with a buddy. And the reason why they partner with something else is because most elements on their own are fairly unstable. And when you partner up or bond with another element or another atom of yourself, it provides some energetic stability. And that is really helpful for all things in nature. All elements seek to be kind of lower in energy if possible. And so when they combine with other elements, it drops their energy, and that's a good thing in most cases for both elements. So when we talk about bonding, the type of bonding that forms depends on the type of element itself, and then also a property called the electronegativity of the element. And this is especially important when we are talking about the difference between an ionic bond and a covalent bond, which is what we're going to spend most of our time on. Now, the electronegativity, it is a numerical value, and what it represents is how strongly electrons are drawn to an element in a bond. So if you look at something and it has a high electronegativity value, what it means is that that element is pulling really strongly for those electrons when it's in a bond with another atom. And if an element has a low electronegativity value, it means that they don't want those electrons. It's not super dissimilar to electron affinity, except in terms of their behavior. So when we look at the values for the electronegativity scale, fluorine has the highest electronegativity and it wants the electron the most. And if you think about it in electron affinity, that's the same thing. Fluorine really wants that electron because it's got almost a full octet, or that full outer shell. It's small in size and all the things we talked about before. However, in the case of electronegativity, it's not measuring just an electron being dropped into the element. It's talking about, hey, I've got two things that are sharing electrons, potentially. How much does that element pull? But the principle kind of still stays the same. On your periodic table, the highest electronegativity elements are going to be fluorine, oxygen, chlorine, and nitrogen. And you want to keep those kind of locked in your head as far as their electronegativity values, knowing that they are big values. And so these elements in this upper right-hand corner here have high electronegativity values because they have big energy benefits if the electrons head towards them. Now, sometimes elements won't just give away their electrons for free. They will share them, and then we'll end up with different circumstances in covalent bonding, and you'll see polar bonds, which we'll get into in a couple days. In general, though, electronegativity increases as you go across your periodic table from the left to the right, and it increases as you go from the bottom to the top of your period. So again, fluorine is the highest. The lowest electronegativity values you can see towards the bottom here are your big metals. And if you think about it, metals don't tend to want electrons in the first place. And we talked about with electron affinity how when you have a big radius and you add something into it, it really doesn't have that much interaction with the protons in the middle because of all the electron shells, and so the energy benefit isn't really there. So these elements down in the bottom left-hand corner here, they don't really want those electrons. When you talk about a bond between two different atoms, the difference in the electronegativity value will tell you in general what kind of bond you have. So if I have an electronegativity difference that is very, very close, I'm going to have we're going to say like between a 0 and a 0.4, and understand that this is a sliding scale. So not everything is going to fit this perfectly, but it's a general rule we follow. If you have a 0.0 to a point, 0.4 difference in electronegativity, you are going to have a nonpolar covalent bond. If you have a 0.5 to a 1.9-ish difference, and that is where things get really fuzzy, is in that upper level there, you're going to have a polar covalent bond. And a covalent bond, if you remember, is where our elements still share their electrons. When you get into bonding between elements that have, and again, that 1.9 is kind of a fuzzy area. When you get into bonds that have differences in electronegativity that are greater than 1.9, you tend to have an ionic bond. And that's because once you get the difference between electronegativity values, and you say to yourself, Adi Meyer, what do you mean? So for instance, let's say we have NaCl. If we find Na's electronegativity is 0.9, Cl's electronegativity is 3.0. And I always just take the bigger number. So if I take 3.0 minus 0.9, that's a difference of 2.1. So we have a very big difference. When you start to get large differences in electronegativity, what ends up happening is instead of the elements still sharing the electrons, if there's a huge difference in electronegativity, the smaller element will actually just give its electron to the element that really wants it with the high electronegativity value. So in the case of sodium chloride, because Na has a 0.9 for its electronegativity and Cl has a 3.0, the difference is big enough that Na will just give its electron over to Cl because it's pulling it so hard. And that is where we get ionic bonds. And so ionic bonds and ionically bonded compounds tend to form these kind of really cool crystal shapes. Even when you get an ionic compound in class, like if we would use it in a lab, you can see it takes on kind of a crystalline shape. They tend to be a little bit more sparkly, and that's has to do with their structure, which we'll get into in a little bit. Gemstones are tend to be ionic compounds, and what happens is the colors that you see in these gemstones actually come from metal ions. Usually it's transition metal ions, so you'll see things like iron and lead and copper that give things these beautiful colors. Like I said before, if we run into a situation where you have such a huge difference in electronegativity, you get an ionic bond occurring. And as a general rule, and this is what I would say, ionic bonds and ionic compounds are formed when you have a metal and a non-metal combining together. That's the rule. So if you see a metal, which if I go back, on our periodic table, the stairs that run kind of underneath boron here differentiate metals versus nonmetals on our periodic table. So aluminum and anything to the left of those stairs is a metal. Your nonmetals are on the right-hand side in the upper corner. And then the things that sit on the stairs are these things called metalloids, which have kind of properties of metals and properties of nonmetals. So anyways, ionic compounds happen when you have a metal and a nonmetal coming together. Just like that's the big thing to keep in your head. And what is different about an ionic compound compared to a covalent compound is that in an ionic compound, the difference in electronegativity is so large that the element just loses, one element loses an electron and the other element gains that electron. So in the case of sodium and chlorine, sodium has a 1 outside electron here. Because the chlorine has such a high electronegativity value, the chlorine is actually able to pull the electron from the Na, and Na becomes an ion Na plus by losing that electron. Cl becomes a Cl minus, and like we talked about with atomic structure, if I have a positive charge and a negative charge and I bring those two things together, they stick together, and that is the ionic bond. So the ionic bond is actually caused by the positive and negative attraction. It is a fully positive and a fully negative ion that are coming together. And because of that, it's an incredibly strong attraction between them. So ionic compounds have very strong bonds between each atom in that compound. And it's very important. What ends up happening is that ions form in a really super organized structure called an ionic lattice. And an ionic lattice this is one example of an ionic lattice, and this is for sodium chloride. So in sodium chloride, it kind of joins its ions in almost like a cubic structure. And so if we look, the greens are the Cl minus and the blues are the Na pluses. What happens is in my lattice, I have a Cl minus next to an Na, and then on the other side of the Na, I have another Cl minus. And so that's kind of how it works, is that they're surrounded by all of the opposite ions and they form this really beautiful structure. And that's where you get those neat shapes that we talked about before. These are some examples of some other structures. NaCl is probably the simplest one, but there are more complex ones that don't look just like cubes. So in the case of, let's say, calcium fluoride, it's CaF2. So you still have these ions all around and surrounding them, but the structure is a little bit more complicated. And this is what gives rise to the interesting crystal shapes that you see. It has to do with their ionic lattice structures. And so you get all these kinds of different shapes. When you go to college, you are going to be expected to know the names of these shapes, but you do not need to know them for AP. So we are just going to go off of the idea of NaCl is our simplest structure. Okay. Now, ionic compounds have some very distinctive properties, and the College Board likes to ask you questions to see if you kind of know what they are. So we're going to go over those, and hopefully you can remember them. So ionic compounds will dissolve easily when you put them into water because of the attraction of water to the ions themselves. If I take a sample, and again, this is our good old friend NaCl here. If I take a sample of NaCl and I put it into water, water is polar, and we're going to review polar, but you've probably heard it before. So water has a partially positive end and a partially negative end. And what happens is the partially negative end of water is attracted to the positive ions in your lattice. The partially negative end of your water is attracted to, the partially positive end of your water is attracted to the negative parts of the lattice. So what you see here, kind of where my cursor or my mouse is a negative ion, that's our Cl. And then the white sides of water, those are the positive ends of the H2O molecule. And so what happens is a ton of waters swarm an ion, and if there are enough waters attracted to that ion, they can actually dislodge that ion from the lattice and pull it away. Now you say to yourself, Mrs. Ademeyer, I thought that they had really strong attractions, and they really do. But if you get enough attractions from the water, you can actually overcome that force, ion to ion, and then you have the water attracted to the ion instead. In the picture in the upper left-hand corner here, you can see the negative end of H2O attracted to the positive ion, and it pulls it off. So what they do is they kind of swarm these ions and then pull them apart. If you have a non-polar solvent like vegetable oil, it doesn't do anything. So if I put salt into vegetable oil, it just sits at the bottom of the container. Okay. Another property that you see, and it's actually kind of interesting, is that if you take an electrical current and try to run it through solid salt, it will not work. You will not get light coming through a light bulb. What happens is anytime electricity attempts to flow, it needs free moving ions to make that happen. And so you say to yourself, well, there's ions in an ionic compound, so why doesn't that work? In a solid, the ions are locked into that lattice structure and can't move. So electrons in electricity don't have the ability to kind of freewheel and move through the solid. But what happens is if you take that and you turn it into an aqueous solution like you see here, or you melt it. When you melt it, what ends up happening is that very organized lattice actually breaks, and then you have free floating ions all over the place. What ends up happening is that molten ionic compounds or solutions of ionic compounds are excellent conductors of electricity, because then your ions are free floating all around and the electrons can move willy-nilly and conduct that electricity. So ionic compounds, and this is a question they really love to show you, ionic compounds as a solid do not conduct electricity, but when you melt them or you put them in a solution, they do. So this is kind of what I was telling you about here. So this is pure water, and pure water with no ions in it will not conduct electricity, and neither will pure NaCl. So if you took a light bulb and tried to run an electrical current through the NaCl, it's not going to work. But if I take the NaCl and I add it to pure water, you end up getting the current. It's kind of like if you would go swimming in a pure vat of perfectly distilled water that has no ions in it. In theory, you'd be insulated and you wouldn't get shocked. But most water has ions like fluorine, fluoride ions, chloride ions, magnesium, and all those different things. And so water is an excellent conductor of electricity, and it's why you shouldn't swim in it when there is lightning. Okay. I wanted to show you a video really quickly of molten salt because I think it's really cool how it works. So, oops, we'll go back. Let's see if this is going to cooperate. So there is no sound, but what they're showing you here is that there's an electrical current kind of flowing through this setup here. So if the circuit is complete, it's going to work. And then we've got some lovely salt coming in there. So you can see that as of right now, there is no electrical current going through. However, you can see as they heat it up, it's going to start to liquefy. And then once we get enough ions free floating and the crystal lattice breaks, you end up getting the electricity to conduct through there. So it's kind of a cool thing. That is a neat property. You have to get it very, very hot to make that happen, though. The other thing about ionic compounds that's important to know is that ionic compounds tend to be hard. So like if you try to squish it with like your finger, you can't do that. But if you would hit an ionic compound with a hammer, it actually would break relatively easily and it's brittle. And it has to do with that lattice structure again. It always comes back to the crystal lattice. So here's our good friend NaCl here. If I provide external force that isn't too hard, like just pushing down on an ionic compound, it's difficult to break. And it's not going to bend. So like I can't take an ionic compound and like bend it back and forth like you could a metal. And we'll talk about that later with metals. So what happens with ionic compounds is that when you apply a force that's big enough to cause problems, you hit the crystal lattice and you snap it. And when you snap the crystal lattice, what ends up happening is that sometimes positive charges now align with negative charges. The lattice normally is positives to negatives and everything is all kosher. But if we have a situation where you have a positive ion all of a sudden next to another positive ion, you know opposite charges attract and like charges repel. So if I have two positive ions that are all of a sudden nestled next to each other, they are going to repel and then they're going to crack. And so that's why you see cracks in crystals, is because when you apply the force, you bring the two similar charged ions together and then they push away from each other, which causes them to be brittle. We are going to be talking about melting points and things like that later on with ionic compounds and something called Coulomb's law, which helps us sort of predict what we're going to see with an ionic compound. So these are just the properties, and we'll get more into what causes some of those properties in terms of their high melting points and stuff like that as we get along. If you have any questions, make sure you pop into a Google Meet and we'll get things cleared up.